psi shown here is the total wave function. Sorry, it is the wave function which is a function of space and time, and H is the Hamiltonian operator, and H cross is H by 2 pi, which is H is Planck's constant. H cross is called Dirac H, and this is how it looks like when you write it down properly, isn't it? So let me go here and start a new page where actually I write down the Schrodinger equation. So what I'm going to write down here now is time dependent Schrodinger equation. I'm not writing the full form. Anyway. So what is the equation? It is I H cross partial derivative of this capital psi with respect to time t, and this capital psi depends on what? In general, it depends on space coordinates. I can call it r, which means x, y, z, and time t. And on your right, you have the Hamiltonian operator H operating on this wave function. But if I explicitly write down this one, I know my Hamiltonian operator is given by minus H plus S square by twice m. It should involve second derivative with respect to space, x, y, and z. But I use this Laplacian square for that. And in general, it depends on a potential energy, which is a function of r as well as could be a function of time t. Okay. Is this clear? Maybe you can write it in the chat box that if you are following. If you are following, please write it yes on the chat box. Okay. Good. Okay. So now let me concentrate on this potential here. Now, this potential energy, okay. So in general, it's a function of space and time. But you will see that in many times, in most of the cases, in the first part of the course, will not consider a potential energy which depends on time. Okay. Now, let me give you an example. For example, if I am dealing with the problem of the hydrogen atom, where we have a nucleus and I have an electron. There is an interaction between them, and the interaction is Coulomb interaction. We'll also discuss that later. But this interaction has nothing to do with time. So, whatever the interaction potential, it is always true. Whatever the interaction now and whatever the interaction after 1 day or after a second, after a femtosecond, so this interaction potential does not change with time. So, for example, if I have an isolated hydrogen atom, so hydrogen atom problem, electron interacting with nucleus, this potential is a function of space only, r. R is the distance between nucleus and the electron. And this is the case whenever we deal with an atomic system or molecular system, which is not subjected to any external field. For example, if I now take the same hydrogen atom and then I put that hydrogen atom in the presence of an external electric field, then what will happen? That this electric field has a space dependent and time dependent oscillation, isn't it? And this will now interact with this hydrogen atom. You can think of more complicated system. You can take a molecule itself, hydrogen molecule, or the nitrogen molecule, and put it in an external field, electric field. And this field will now interact with the electron in the system. And in that case, your interaction potential will be now function of not only time, space, but it's going to be a function of R as well as T. And this is the case when your atomic system atom or molecule, whatever, that is what you do deal in molecular physics or in chemistry, is exposed to external field. Now this external field is actually an electromagnetic radiation. This could be electrical or magnetic, electric or magnetic. Sorry. And what is this? This is the case of spectroscopy. This is essentially what we call spectroscopy, isn't it? Spectroscopy, what you do, you take a molecule or an atom, and then you expose that molecule or atom to an external field, isn't it? So this is what you deal in spectroscopy, which you will do later, not now. So for the time being, we consider a case where my potential V does not have any time dependence. So it is actually, it has only space dependence. Only on space coordinates. Okay, so I have a case where your potential energy is a function of space coordinate only. And if this is the case, then see what happens with this case. Actually, it is possible. Now, for example, if my V is function of R only, then it is possible. To solve this equation, this time dependent equation, by assuming that, okay, my wave function, which is a function of R and T, can be written as product of two functions, and a small psi, which is a function of R only, which is a function of space only, and then another function capital T, which is a function of time. So this small psi is a function of space only, and this capital T is also a function, but it's a function of time only. So if I invoke this structure, that my total my wave function capital psi, which is a function of space and time, is written as a product of a function which is a function of space and a function which is a function of time and only space, then it is possible to solve this equation. Okay. So I will do that. So for simplicity, we will consider a case which is one dimensional. We can do it in 3D. Basically, so consider a one-dimensional problem. So basically, I have only one dimension, say, call it x. If it is the case, then what is the Schrodinger equation? I have the Schrodinger equation is I h cross, and this is a function of x and time t. And you see, this is a partial derivative in time because it's a function of space and time, x and t. That's a partial derivative. And wait. Yes. And this is equal to minus h cross a square by twice m. But since I am considering a one-dimensional case, I have only one space coordinate, which is x. So I'll have this, and my potential now depends only on space, which is b of x. Now the whole thing is now operating on capital time, on capital, which is a function of x, as well as, okay. But I told you that, okay, we are invoking this, that the capital psi can be written as product of a function which is small psi, which is a function of x only, times another function capital T, which is a function of t only. Okay, and then what I do, I just take this, and I put it back in this equation. When I put it back in this equation, what I'm going to get? When I put it back here, I'm going to get I h cross del t of the function which is psi of x times capital T of small t. Okay, and this is equal to whatever minus h cross square by twice m. So you can see that Hamiltonian operator now depends only on space. There is no time dependence of the Hamiltonian operator. The Hamiltonian operator, which is only space dependent, that operates on this psi x time t of. Now what is going to happen? The left hand side, just see. It is, if you see carefully, you will see that, okay, this is a function of x only, isn't it? The Hamiltonian is also function of x only. On the left hand side, this t of t is a function of time t only. Okay, so that will help, isn't it? What I'm going to do now, if I proceed further, very easy. What I'm going to get the left hand side will give me I h cross, which is a constant, but the time derivative, the partial derivative in time, will operate only on this function t of t. It will not operate on the function psi of x because this is time, there's no time dependence. I can take it out like this, and what I have here is this partial derivative with respect to time operating on the function capital T, which is a function of small t. And what will happen to the right hand side? So this is your h, isn't it? I don't want to write it again and again, but it's a function of x only. So h is a function of x. Just to denote, but you know, Hamiltonian operator depends only on x. So what is going to happen here, because it will operate only on psi of x, it will not operate on t of t. So t of t I can put it here, and then you have a situation that H that operates on psi of x. So any questions? I think this is quite straightforward. I think it is very straightforward. So maybe I'll proceed for a few more minutes, and then when I get the solution, you can ask questions. Okay. Okay, just write in the chat box that you are following. I hope you are following and you are there. Good, 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 good. Yeah, very good. So now what I'm going to do, I'm going to do something. What I'm going to do now, you can divide the whole thing, say left hand side and right hand side, with this uh, function psi, the total function psi of x comma t. And if I do this, what I'm going to get something like I h cross I have psi of x, and I divide the whole thing by, say, psi of x comma t, which is psi of x times capital T of. If I do this to my left hand side, I should also do this to my right hand side, isn't it? In the right hand side, what I'm going to get this divided by psi of x comma T of t, and then this Hamiltonian operator operating on psi of x. Here, and now what I can do, so let me write down, so dividing both sides by sometimes I by okay, this is what I do. Now just see what is going to happen now. See, I can actually cancel this psi of x on your left, isn't it? I can just cancel this psi of x. On the right hand side, what I can do, I can cancel this. So what I have now, I have the following equation. What I have here is now I h cross divided by t of t, then del t of t, del t, that is equal to 1 over psi x times h operating on psi x. So we have an equation. We're equating something with another thing, no, isn't something else. Now again, see carefully. What is there? To see carefully that whatever is there on your left, it depends only on what?
Time.
Only on time, yes. What about things on your right? Whatever is there, it depends only on space. On space. But you are saying, okay, something which depends only on time is equal to something which depends only on space. This is possible when? Can anyone tell
When
me?
both are equal to some constant.
Yes. Who is this?
Sir, I'm Rohini.
Okay. Rohini, you are in which course? 425 or 812?
Sir, 812.
812. Okay. Someone from 425. Someone from BS. Can you answer? You have something which depends on space equal to something which depends on time. when it is possible. Anyone is there from BS? Can you write it down? Devojit, others, Akash, oh, where are they? Yeah, so it has to be equal to something, a constant which has no space or time dependence. So, and then what I'm going to do, for some reason, I'm going to equate this to a constant. I'm calling it E, capital E, a constant. For the timing, call it a constant. This is here. So what I'm now going to do, I'm now going to solve this equation. So now I have two equations, one which depends on space and one which depends only on time. So let us try to solve this. Okay, so let me solve the time dependent equation first. What is the time dependent equation? We had something like I h cross divided by, I think, T of t, and then we had this is one equation, and the space dependent equation was what I have now. Okay, so let me try to solve the time dependent equation, which only depends on time. Now a careful examination will tell you that, okay, you don't need to write a partial derivative because it is no longer you have space involved there, you have only time. So strictly speaking, no partial derivative is required to represent. No partial derivative, then you have IH cross divided by T of t, and you have okay. And now what I can do, I can just solve this. If I solve this, what I have here is essentially I have this. Can anyone tell me what is the solution? What will be the solution for this? Can anyone tell me what?
ln t is equal to E by iota k.
Okay, okay. Ln t of t equals to E by
Iota k.
I h cross. This is not k. This is h cross.
Sorry. Yeah. And then we can write it minus E iota by h cross. Sorry.
That will do later. What I have here is
t will be exponential of minus iota E by h cross.
okay. So what I'm going to go get something like E by I h cross, but don't forget I'll have a constant. So call it C1. This is fine. This is fine. I have missed something here.
Hello, sir. DT is.
I,
Yes,
yes,
sir. D,
what I have missed?
yeah,
What I
sir.
have missed
E,
here? What I have
DT,
missed here?
EDT, and then and T term
ET
is
by
coming
IH.
in the ET by IH cross,
I
and then plus.
integrate from say 0 to t, isn't it?
Yes, sir. Yes.
So I missed this capital small t. So
Sir,
now this is
sir,
fine.
in the
Yes.
here is also the DT term also come in the DDT of DT equals to
Yeah, yeah,
EM.
yeah. Yeah, yeah, I
Here.
know. Okay. So let me do one thing, that E by IH cross, what I can do, I can write it as, I can multiply with E in the numerator, also multiply it with E in the uh, denominator. It will give I square H cross. What is I square? What is the value of I square?
That's one, sir.
Minus
I
1.
square is
Minus one.
minus
Minus 1.
1. So this will give me minus I E by H cross. I like this form for some reason. So I can just write it like minus I E by H cross times T plus some constant C1. But now what I can do, I can just take anti-log. What I'm going to get something like T of T is equal to exponential of, what is that? Minus I dt by h by, sorry, h cross should be there, sorry, sorry, typo. So this should be h cross into time t, and then I have c1, which is nothing but exponential of c1 time exponential of minus I dt by h cross. Now what is exponential of c1? This is also another constant, isn't it? Yes, you unmute your thing. Yeah. Another constant. Somebody has a background noise. Please unmute. Sorry, please mute, not unmute. Unmute. Okay. I'm calling it A. So what I have here is T of T equal to capital A times exponential of minus I square dt by H square. Okay. So we have a solution for this problem. So now I have a solution for this problem. I have a solution for this problem. And somebody, hey, who is having the microphone on? Please switch off your microphone. Yes, thank you. Yeah. So this is the solution I have already for the time dependent part. And what I'm going to get, I'm going to write it down here. And just okay. And I come back here. This equation I can rearrange and write it in a way that maybe it is familiar to you, some of you. So this equation, I'm calling it H as right. And this equation has a name. Maybe people can write it down the name in the chat box. Can you write down the name of this equation in the chat box? And meanwhile, I write it down here. Yes, time independent Schrodinger equation. Yes. Okay. known as eigenvalue equation. Okay. So what I have here, end of the day, I have a solution like this at my psi of x comma t is given by psi of x, which I should get when I solve this equation, which I have not solved, time, and then I have a constant a. Okay, so a times exponential of minus I t by h square. But you know that there is something called normalization, because you have to normalize the wave function. Your wave function, this capital psi star psi, when I integrate all space a minus infinity to plus infinity, and that should give me 1. This is normalization, isn't it? So end of the day, I have to normalize the function. This is the normalization condition. So essentially, you have an integral over x. So it will not affect the time dependent part. So what I can do, I can actually, what I want to do, this constant, you can see the constant here, this a constant shown here. This constant I can absorb in psi of x, because it is just a number, because eventually I am going to normalize psi of x, that will give you a normalization constant. So this constant a, I don't need to write it here explicitly, I can absorb it here. And if I do so, my solution, my general solution, not general solution, the solution I'm writing it here is going to be this. So your psi of x comma t is going to be equal to psi of x into exponential of minus I t. Okay. Any question so far? So how many of you knew about this? Just starting from time dependent Schrodinger equation and then getting this to equation and write the solution as a product of space and time part. How many of you knew? Write it in the chat box. Okay. Akash. Okay. Oh, what about students from BS? You must have seen this in page 107, the BS students, past year. Hey, who taught you CH 107? Remember? Okay. Shuddha Sattva sir taught you PH 107, not CH 107. Shobna, yeah, Shobna. Yes. Okay. So now you have it here, but it is not complete. Now let us do something else. Now, as I told you, remember third postulate. What is the third postulate? It says that if I make a measurement, each time I make a measurement, I get an eigenvalue of that corresponding operator. So for every measurement, I have an operator, every observable, and whenever I measure that observable, I end up getting an eigenvalue of that observable, that operator, isn't it? So what does it tell you? It tells you that, for example, if I have a case that I have a function, a function psi of x, actually, if I try to measure, for example, the total energy, H is a Hamiltonian, so I try to measure the total energy. So if I measure the total energy, then each time I measure, I'll get different values of the energy, isn't it? And these are eigenvalues. I may get the same again and again, but I'll eventually get all the eigenvalues if I make many measurements. So these are the eigenvalues, and the operator is your H. And the wave function for that eigenvalue is be the eigenfunction of that operator H. So I'll denote this as psi1x, psi2x, psi3x, and psi4x, and so on and so forth. Okay. Now consider a simple case. Consider a case where you have the two eigenvalues, E1 and E2. And then you have two wave functions, psi1x plus psi2x. And then you solve the Schrodinger equation, time dependent Schrodinger equation for this. And then I ask you to write down what is the wave function. Now you write down something like this. Okay, this could be something like psi1x times exponential of minus I E1t by h cross. I can put a constant here, C1, which will take care of my normalization, and also it will be quite useful. I do not next. But also there is another possibility that I have a function which is something like C2, some other constant multiplied with psi2 x exponential of minus I E2t by h. Okay, so then what is the general solution? The general solution in this case, I can take this, this is one solution, this is another solution, this is one solution. Solution means one possibility, this is another. And you'll see that if I take these two and add them, this is called linear superposition essentially. If I take a linear combination, so if I add them like this, the whole thing is also a solution. So let us check this, whether this is true. So what was my equation we had started with? My equation is this, I h cross and then I put this here. So on your left hand side, what I'm going to get is this I h cross del t operating on this function, which is C1 psi1x exponential of minus I E1t by h cross plus C2 psi2x exponential of minus I E2t by h cross. What I'm going to get, see, it is a derivative with respect to time, so this part will be unaffected, only it will operate on this time part. So I'm going to get I h cross, I can take this guy outside, psi1 x and C1, and if I operate this on exponential of minus I et by h cross, I am going to get minus I E1 by h cross into exponential of minus I E1t by h cross. What is the next term? Next term is going to be plus again IH cross C2 psi to x into minus I E2 by H cross into exponential of minus I E2 t by H cross. Okay, you are following. If you are not following, please write. And if you are following, write yes, yes, I am following in the chat box. Please write that you are following. Okay, good. So now I just further simplify this. You can see that this H cross and H cross will cancel, and then I and I will give you minus I square, which is 1. So essentially what you have here is C1 E1 psi 1 x e to the power of minus I E1 t by H cross plus C2 E2 psi 2 x into exponential of minus I E2 t by H cross. Okay, is clear? And what about the right hand side? What will happen to the right hand side? This is the left hand side, no? What will happen to the right hand side? And the right hand side is this. Your RHS is going to be your H psi equal to E psi kind of thing, isn't it? So your H is whatever the H is, H operating on C1 psi 1 x okay, and this one is obvious because when H operates on psi 1 x, it will give me, because I have this equation, because I have H operating on psi 1 x giving me E1 times psi 1 x, H operating on psi 2 x, I will be E2 times psi 2 x. Okay. So what I'm going to get here, it will give me nothing but C1, then E1 times psi 1 x, and there will be time dependent part as well, plus C2 times E2 psi 2 x. Somebody asked me a question. Yeah, same. So what I'm going to get here now, see what we have now. What is there in the left hand side? See what is there in the left hand side. This one is actually equal to this. So what I have proved here that whether this is one solution, this is another solution, but if I add this to solution, that is also a solution to time dependent Schrodinger equation. Is a solution for the time dependent Schrodinger equation. Is it fine? Any question? If you have question, please tell me. So let me write down again. So what we had here had as follows. Okay, my function psi of x comma t, earlier we had written down it as psi of x at the power of minus I e t by h. We'll come back. So if I take this as my solution, and then I consider, because this is for one-dimensional problem, and I consider one-dimensional problem, and I consider just a minute. Take this, and then if I consider, this is essentially one-dimensional problem, and okay, I have the particle in a one dimension, and if I assume that I have a position like x, and then here x plus dx, so this gap is dx, this displacement, then what is the probability of finding the particle in the length dx? Within dx. The answer is as very simple. I take the wave function, take a complex conjugate of that, multiplied with the wave function, and then multiplied with the length dx, this one. And if I take your psi of x comma t as this, in this case this is going to be psi star x into okay, I'll just take psi of x into to the power of minus I e t by h cross, and you have to take the complex conjugate of the whole thing multiplied with psi of x exponential of minus I e t by h cross into dx. And what is the answer? Because if I take complex conjugate of this thing, what I'm going to get psi star x, and then I have to take the complex conjugate of this, like exponential of minus et by h cross, complex conjugate of that, then psi of x, then exponential of minus I et by h cross into, not complex conjugate, this one is fine. Yeah. And what is the complex conjugate of exponential of minus I t by h cross? You know, this is psi star x into exponential of plus I e t by h cross, and then psi of x, and then you have exponential of minus I e t by h cross dx. And these two will combine. What will give? It will give me 1. This two will combine, and this will give me exponential of 0, which is equal to 1. Okay, and it will give me 1. So what is good about it? Good about it is that what is here, the whole thing, what I'm going to get here is psi star x some times psi of x dx. This is time. Hence, if I have a solution in this form, this represents a situation where my state, the probability associated with that state is time independent, and this is called stationary state in quantum mechanics. So this represents what is known as stationary state. Okay, any question? I'll take a break. Any question? Ask me. You can now unmute yourself and ask a question if you want.
Hello, sir. This is Ramanan.
Yes.
Yeah, if we take the linear combination of two energy state, then what happens? It will be remain as a stationary wave, or will be something else?
Yeah. So the next thing is that it will not be stationary. It will be non-stationary. It will do it.
Okay.
But if I take only one energy state, as I showed here, then this state is stationary because the probability or the probability density associated with this state is time independent. Although the wave function has time dependence here, but psi star psi has no time dependence. So that's why it is uh, called stationary state. Now also you can do another thing. For the stationary state, you can actually calculate from any average, for example, expectation value. So if I calculate an expectation value like this, for example, any operator A, the expectation value of A is what? You know the answer, it is x comma t star A and what is going to happen to this? In the denominator, you know what is going to happen. In the denominator, this one I have already showed you that this is going to be, if I take this, this is nothing but your small size this is time independent. What happened to the numerator? Numerator is this dx. Now psi star, I am now skipping few steps because you know this. Psi star will give me psi star x into exponential of plus IE1, sorry, IET by h cross, and then I have the operator a, and then again psi x exponential of IET minus IET by h. And you know that that operator a is something like, it will be like position operator or momentum operator or Hamiltonian, for example, and it has no time dependence in general, isn't it? So as a result, what I'm going to get here the numerator itself, so this thing will again cancel. This, the whole thing is going to be time independent. So any average value or expectation value I calculate for such state, so that is time independent. So that's why it is also called stationary state. So if I calculate the total energy, which is where I have to choose A as your Hamiltonian operator, then the total energy of the system is not going to change. Whatever the energy now, the energy will be the same after say 10 days or after 1,000 years. So that's why it's called stationary state. Although the wave function is time dependent, the probability density or any average value you can calculate has no time dependence. Is this clear? It's very important because this is essentially you will deal with this in the first part of the course. And as Ramanand was asking, he was asking that if what I showed just a few minutes back, that you can take two states and then you can linearly combine them, you can add them and get a solution, which is also a solution to your time dependent Schrodinger equation. In that case, whether that represents a stationary state, the answer is no. The answer is no, and so we'll just show this here. So what I'm saying that, okay, in general, the general solution is, I already showed you that I can have a solution like C1 times psi1 x into exponential of minus C1 t by h cross plus C2 times psi2 x exponential of minus C2 t by h cross. But again, I can have other terms, no? Why should I stop with two terms? I can have infinite number of terms. So in general, I can have a solution like this. which I can write it as I have infinite number of terms. We'll have something like Cn is a coefficient and psi n x is a function of x. Okay. So this is general solution. To time dependent Schrodinger equation when v of x comma t is actually v of x, no time dependence in the potential itself. Okay, and as Ramanand was asking, where I write my wave function as a product of a space part and time part, this is called separation of variables. And this is only possible in this case when your potential limit does not depend on time. Okay, so v of x comma t has to be only v of x, no time dependence. Okay, if you have time dependence, you cannot use this technique, the separation of variables. And in quantum chemistry, mostly when you deal with energy problem, calculating energy levels and other things, we deal with boundary value problems. We have a boundary and then we deal with boundary value problems. It's a with time independent potential energy and boundary value problems. This is a technique used. But again, even with time independent potential energy, there is another way of solving that equation. Okay, but that is called initial value problem, which we will not discuss in this course. Okay, that is different. We can discuss later, privately or maybe in a different session. But this is how we are going to do it. But when you do spectroscopy, maybe we will do, I'm not sure. Rahul will get some time for time dependent perturbation theory in this course.
Difficult. I mean, extremely difficult. We'll try to the later part. But time dependent perturbation theory, I didn't thought of that I will be teaching this time.
Yes.
Let's see if time permits.
But briefly, maybe you can mention this qualitatively.
Yeah.
So what is going to happen that then your potential energy will have a term which is coming from outside because of the electric field, and it will have a time dependence. So in that case, you cannot use separation of variable. You have to use a technical perturbation technique. Okay. So Orko, is that was your question?
Yes, sir. Okay, sir.
Yeah. So, but this is, you remember that this is with v not dependent on time, depending on only position x or in steady on r. Otherwise, we cannot use this technique. But again, you remember this is not the only solution. Even with v does not depend on time, it is possible to find other solutions which are called initial value problems, which we will not discuss in this course. This is beyond the scope of this course. But we will stick to this separation of variable technique, and we'll do. Okay. It works. Actually, it is something like you divide and conquer kind of thing. You divide the solution into product of two, and then you get the solution. So this structure you should remember. So far you have done the postulates and arrived at time independent Schrodinger equation from time dependent Schrodinger equation. So essentially what I have here now is this as follows. For the next few classes, we'll consider this equation. And we'll solve this equation for few cases where this can be solved exactly analytically. Okay. And let me briefly start discussing a problem which you already know, but maybe we'll start again. So I can think of a one-dimensional motion of a particle. I have a particle, but say this particle say have a motion in 1D, and it can be found say between x equal to 0 and x equal to L. it cannot go beyond L, or it cannot go on the left to the x equal to 0. So this, let me illustrate this. So what I am saying here is as follows. So I have a particle. So I have say, in one dimension this is x, and then you have a point. This is x equal to 0, and then you have another point x equal to capital L, and the particle can be found only between 0 and L. And so, and also we assume that whenever the particle is between 0 and L, the particle, whenever, so essentially the potential energy, which is a V of x, is actually 0 when your x is within, x has to be within this. And if it is anything other than that, your potential energy is very, very high, and I call it infinite. So essentially what you have here at the boundaries at x equal to L and x equal to 0, these are boundaries essentially. You have a potential energy which is something like, when like this, it will go to infinity. Sorry for very bad drawing. Okay, so this is G, infinity. And inside this, we, okay, and this is one dimensional problem. And if you see any book, it is called particle in a box problem. You know, all of you, I think. Please write it in the chat box if you know. It's called particle in a box problem. Okay. Can you write it down in the chat box that you know? Yes. Yes. Okay. So, but why would I do such problem? Because this looks very unphysical, because I have a potential energy 0 within a length L, and beyond that L length, the potential energy is infinite. Whether you can have such a situation. So let us try to find a chemical system where you can have a situation like this. So let me write down, you know, this conjugated systems from organic chemistry. Because end of the day, this is the quantum mechanics course for chemists to bring chemical examples whenever it's possible. So let me write down a conjugated system. So I say I write down this. Okay, so I have how many carbon atoms? 1, 2, 3, 4, 5, 6. Okay, and then I have to put one H here, then one H here, and then what is that? One H here. Okay, what is the name of this molecule? At least people who are from chemistry background should be able to tell me what is the name of the molecule. How many carbon atoms are there? Write it down, the name of the molecule.
Hexatriene.
Hexatriene, okay, yeah, right.
Hexa 135 triene.
Yeah, hexatriene, okay. And if you ask an organic chemist, he would tell you, definitely, he or she will tell you within a second that, okay, these carbon atoms here, these are sp2 hybridized, isn't it? You know this? Physicists may not know, but a chemist would know, are sp2 hybridized. Okay? So if it is sp2 hybridized, you know that there are 3 covalent bonds for sp2, but then there is a vacant p orbital on each carbon atom, isn't it? And this vacant p orbital on one carbon atom and another vacant p orbital on the adjacent carbon atom, they will form what is known as pi bond. You know that. So if I draw this, essentially what I have here, maybe I'll use another color. Shown here. So essentially on each carbon atom I have this. This p orbital with one electron, isn't it? And this orbital can overlap and form a pi bond. But actually on this p orbital I have one electron, isn't it? Are you convinced? This is your chemical knowledge will tell you that you have one electron on this carbon atom. And now if I can think of that electron on this p orbital tries to move along this chain, because delocalization means what? The electron is everywhere because of this pi bonding. The electron on carbon atom 1 is also localized to carbon atom 6, isn't it? It's delocalized all over the space. That is how it is. Are you convinced what I am saying? Please write down in the chat box.
Yes, sir.
Yes. So now just think of, if I ask you to draw the potential energy of this system. The potential of the electron felt in that system. So if I write it down, you'll see, draw it. It is obvious that when the electron is far away from the carbon atom, it will have a higher potential energy. But when it comes close to carbon atom, it will feel lower and lower potential energy because there is attraction between the carbon nuclei and the electron. And it will go negative. It will go to the negative. So essentially, it will start like this. And then when close to carbon atom, it is negative. Again, when it starts going away from this carbon atom and towards the other carbon atom, its potential will increase, and then increase, and then again when it reaches the second carbon atom, the potential will go down. So it will repeat like this. I think I draw one less. I should have drawn one more. So how many are there? So there are 5 bonds. So I think I should have one more. Yes. Draw it here. It goes like this. Here we have a deep. Deep. So this is how it is going to look like, isn't it? The potential energy felt by this electron because of this carbon nuclei. 1, 2, 3, 4, 5, 6, 6 nuclei. Okay. So here the energy is negative, and here the energy is positive, but here the energy is quite deeply negative, it is quite positive. So what you can do here, this does not really represent this box, but a very, very, very crude approximation of this would be something like this, because you can see that although energy is negative here, this barrier is not very high, because it can easily go from one point to the other point. So I can say, okay, and crudely I can say it is something like this. Are you following? Because these barriers are not very high, so I can approximate these 6 points with a flat potential like this. But then you have, if the carbon wants, the electron wants to go outside the molecule, then there's a high barrier which is shown here, this one and this one. Okay. So ideally, I should have a situation, if I further simplify, I have a situation like this and this and this. But again, this is finite in reality. This is finite. But so for the timing, I assume that this is finite, but large. And then for the time being, I assume this to be this part, the potential energy becomes very large, infinity. And then it will represent the case I shown here. You are following? Please tell me whether you are following.
Yes, sir.
Because I want to give an example from chemistry, because it is important that I give example from chemistry, because initially it's a chemistry course. But I don't believe, personally don't believe there is something called chemistry, physics, biology. I believe that nature behaves following some rules, and we are here, all the scientists are here to understand how the nature behaves, isn't it? And then we have categorized this into physics, chemistry, mathematics. Okay, so now let me go back. Maybe I'll discuss for 5 more minutes and we'll stop. So essentially what I have here is this problem, and I can now split this problem into 3 regions: region 1, region 2, and region 3. In region 1 and 3, the potential energy is 0, and region 2, potential energy is infinite. Region 2, potential energy is 0. Okay. So so in the region 1 and 2, if I write down the time independent Schrodinger equation H psi of x for this problem, and if I ask you to solve this equation for region 1, not 3, 2, 1 and 3, what will be your answer? So the answer is as follows, because you see that in this region your Hamiltonian has a potential energy which is very large, isn't it? So a very large quantity multiplied with something psi of x gives you something on your right hand side which is finite, because and this is possible only when your psi of x is 0, isn't it? So in region 1 and 2, psi of x has to be 0. In other words, because the particle is confined within the length 0 and L, it cannot go outside if the potential is very, very large. So the wave function of the probability, which is psi star psi, of finding that particle in region 1 and 3 is 0. So the wave function is 0 in region 1 and 3. So this actually brings you that you have to solve this for the region 2, and for that v of x is equal to 0. You don't need to solve it for region 1 and 3, because you know that the function is 0. And in this region, your Hamiltonian is going to be like h cos square by twice m d2 psi x dx square equal to e psi x. Psi x, and because your potential is 0, there is nothing called v there in the equation. So what I have here is minus, I am calling it say psi x, okay, is some constant. So what I need to do, I need to solve this equation. What is that equation? This equation is shown here. The equation I need to solve in region 2. Okay. This is your time independent Schrodinger equation for region 2. And we will solve it with the boundary condition that your wave function psi of x equal to 0, because it should match with the wave function in the region 1, so it has to be equal to 0, and psi of x equal to L, capital L, is also 0. And these are the boundary conditions. With these boundary conditions, we are going to solve this equation, but we will do it in the next class. So we'll stop now, okay, and I'll stop sharing the slides, okay, and in the next class we'll start solving this equation. This is called particle in the box equation, and from there we'll go on further. And then my plan is to do harmonic oscillator and then hydrogen atom. And meanwhile, I talk to Rahul, because we are planning a quiz. So there will be one quiz and one midterm exam. This is what I plan, but this is not final. It can change. And you can also have a situation that you have a surprise quiz. So please come and attend all the classes. Very important that you attend. Unless you have a situation where you cannot attend. Okay. So what I'm going to do now, I'm going to now stop sharing. Stop sharing, and also I think I will, maybe I continue. There's a question. The question is, let me read out the question. Akash is asking a lot of questions regarding the previous day class. A term comes which is the Hilbert space in the statement of postulate 1. I did not mention Hilbert space in the postulate, but I said, okay, there is something called Hilbert space which we will discuss later. So we'll answer this question later.
Okay, sir.
Because I want to make it simpler. When you deal with vector space, we can deal with Hilbert space. Rahul, what do you say? Maybe we can discuss later.
Yeah.
Rahul,
okay.
Are you there?
Yeah, I'm there.
Yeah. So
actually, sir, you have shared a book. In that book, in the postulate 1, there is mentioned that term. That's why I asked.
Okay. But the postulate, the one I wrote, I did not mention that word actually.
Yes, sir.
Even without that word, you can understand what I meant. Yeah.
Okay.
But if time permits, we'll discuss this.
For particularly this one, it needs some prior concept. For example, vector space.
Yes.
Yes.
So without this concept, so you see that in these mathematical things, you always need too much prior concept to go over to the exact what the definition is. So basically, if you want to know the Hilbert space, you need to have the knowledge of your vector space and Euclidean space.
Okay.
And this is getting too much this gets too much mathematical. We don't have the expertise. Very, it's not exactly needed also in right now. You see that the vector space is kind of, the Hilbert space is kind of a vector space where you
actually. You're right.
Complete in one sense. Which is complete in one sense, and completeness relationship probably Rashid you have already discussed, right?
What I plan to discuss after 1D box, maybe we will just go back and look into what is known as the properties of Hermitian operator, which we have now discussed.
Yes.
So
you have not till now discussed probably the completeness of the eigenvalues, right?
Yes.
Eigen functions. Have you discussed completeness?
No.
Okay. So
not explicitly.
It's getting difficult to discuss Hilbert space also.
Yes.
Okay, sir.
Yeah. But we'll do. It is like a detouring from the core, from the flow, and then do it and then come back. Okay. So what I'm going to do now, I'm going to stop recording. Okay, but square root. Okay. I just call it k square.
Yes, sir, in last slide.
Yeah. I just call it k square. What is the problem? K square is 2me by h cross square. Any problem with that? No problem. I don't see.
Oh, don't worry about this constant.
Yeah, it's a constant. I'm calling it k square. You can call it a constant c. Yeah. So okay, I'll stop recording now.